Hello. So this is the UP induction, and the topic I'm covering today is graph problems. That is the general area. So I think it's important that at the very start we go over what graphs are and the different types of graph problems. Afterward, I will go through some very basic approach and maybe algorithm that you will find very useful in solving graph problems. All right. So to start, let's determine what exactly is a graph. So on the left, you see a very, very formal definition of the graph. I believe you can read that by yourself. But essentially, the graph basically contains a non-linear data structure where you have these different vertices and connected to another vertices by edges. And I think one of the most common example you can think of is probably a tree or binary search tree. Binary search trees and trees in general are a type of graphs. But for example, on the right, you see that we have this figure here. This is obviously not a tree, and this is what we'll call a more general form of graph, where you have like 0 to 4 vertices connected to each other through these edges. Um, and we can sort of think of these as different pairs, or sometimes in graph problem it's good to think of, you might want to group the connected nodes together. You might want to store the different vertices along with their edges. Um, there's a lot of different combination of data structure that you can store them with, but let's go ahead and go to the next step and talk about what exactly the graph problems are used for, and maybe some things you might be asked to calculate in terms of the problems you'll see. Um, so over here, you see a flight network of, in this at the United States, and immediately you can sort of see that um, you can represent the different airports as different vertices, where the flight path connecting uh, the airport will be what the edges are. So for example, you see that the blue dots are the smaller airports, and once you hit red, it's like a major airport. And here are the routes. And some of the problems you might face is, okay, maybe you need to find a path from, let's see, Denver. I believe that's Denver to Atlanta. Or maybe if you're doing a longer travel, you might start from the city in Florida, and you had to find a path to Los Angeles. Or if you start from a very, very tiny airport, like let's say this one, you might have to calculate and find a path and see which transfer you're going to have to take in order to reach a major city. And among like just finding the path might not be enough. Sometimes you'll be asked to optimize the route, maybe use some simulating annealing, maybe use some A star to find the path. Or let's say today you want to visit every major city in the world, then it will be called a traveling salesman problem, and that by itself will be a graph problem. And that's actually a very good problem if you want to look into it. Um, I do know that problem is like very, very complicated, and there's multiple ways to solve it. Um, but yeah, this is essentially what graphs are for. There are other applications for it as well, such as if you're just storing data. I think some encryption methods do also use a graph, but it might be more specific to a tree structured graph. All right, so let's go ahead and move on. So over here are some of the LeetCode problems you can check out. Um, I have wrote a discussion post on them that you can find, or in general, you can try them yourself. And I will go over uh, the maximum level sum of binary tree at the very end if we have time. But I don't think we do. And on the very bottom is a very nice problem I found on YouTube. It's done by the CEO of Algo Expert. It was a high school student. Essentially, it is a Google interview problem where you're given a set of airport and their connection flights, and you want to find like how many edges do you have to add in order for every single airplane or every single airport to be connected to every other. It's a really neat problem. I highly suggest you check it out if you have time. All right, but that's enough for the problems. So to start with the graph problem, let's say today you're going to be asked to find the shortest path. There's multiple different approach to it, but the very, very first important part is how exactly do you represent graphs? Like, is it going to be, are you going to be given like a root pointer, like in a binary search tree, or a binary tree, or a tree in general, where you're going to have to traverse through it, or does it come in some other form? And most of the time, it will come in the form of an adjacency list, where it's you'll be given a list of for every single vertices in the graph. So let's say we go back to our first problem. You'll be given 0, 1, 2, 3, 4, and then for each of those it will most likely be like a hash table or a dictionary. And if you're using Python, 0 will be have 1 and 4. Essentially, it will just the list itself will contain the node or the different vertices it is directly connected into, or the vertices it has an edge with. So that is what an adjacency list is. Another representation you can encounter for graphs is an adjacency matrix. And sort of imagine there's a 2 by 2 matrix, which or n by n matrix, where the rows and the columns are marked by the different vertices. So let's say you have 0, 1, 2, 3, and then you have 0, 1, 2, 3 on the top. Then if you have a vertices, or if you have an edge between these two vertices, what will happen is at 0, 1, it will be marked, it will hold the value true. An adjacency matrix is a Boolean. It's essentially n by n matrices with booleans that shows you which edges are connected, where like the rows and the columns represent the different vertices number. Um, yeah, so then let's go ahead and sort of dive deep into the different way of traversing the graph. So most of the time when you look through graphs, you're going to traverse them in order to, so let's say you're trying to find a path or a most fitted path algorithm, you are most likely going to have to go through the graph. Let's say you're just trying to find a specific path through a maze. You're going to have to go through the vertices and then try to hit the end somehow. And the most two common approach is called the depth first search and the breadth first search. They are very, very similar to the depth first search and BFS for trees. It's actually the DFS and BFS for trees are derived from these two forms, but we'll be covering on how do you do these in the sort of a general form, and maybe some modification you're going to have to make for it to work with your specific problem. So first, let's cover depth first search. The very first thing you want to think about when you, you see a pathfinding algorithm and you want to decide that you want to use a depth first search is you want to think about the stack, because that will be the main data structure for you to push in vertices and pop them out in order to construct this. Um, oops. And essentially, depth first search is you go as deep as possible and in a straight line. You do not consider other option, and you go until you hit a dead end. If that dead end gets you to the destination, great, you're done. If that dead end doesn't get you to the destination, you go back and retrace until you hit it. So one of the example for one second. One of the example I'll go through is, suppose you start from the source and you're trying to hit the destination. Um, for with a depth first search, what you want to do first is you'll start from the source, and you have your stack, and you'll begin pushing these blocks in. So you'll push this block in, or first you'll start with the source. You'll push the source in the block. You'll pop it, and then, or you'll pop it to examine it. You'll find that, oh, it has one adjacent block, and then you'll push this into the stack. And since the stack is not empty yet, you'll continue the search. Eventually, if you continue this pattern, you'll eventually hit this specific block. And here's where the depth first search differs from the breadth first search. So in this block, what you'll do is you'll actually push, before you examine this block, examine every single possibility of this block. You will simply take, so this block has two different edges. You have the block over here and the block on the right. So you actually push the block on the left or the right, depending on whichever. So let's say in this case, we go to the one on the left. You'll push this onto the stack, which then it will examine, find that it has no vertices around it. and then it will realize, oh, this is a dead end, and then it will continue to loop. But in this case, the stack is not empty. So then it will, after it push this off, it will go back to examine this specific block. This specific block in turn will examine this block, which will then get you to your destination. Um, yeah. So, but let's say this block does not succeed, then what will happen is this block will be popped off and it will sort of go backward until we go back to the source, and then that's when I realized, oh, the stack has returned to zero, and we don't have a valid solution. In this case, in that case, then you won't be able to get to the destination. Another really important uh, concept about graphs is there's a very high chance that there is a loop within. So let's imagine this block, and this block has been colored white. So what will happen in this case? You will end up having a cycle, and if you have a cycle and you use the stack to traverse it, there's a good chance you'll end up in an infinite loop where it will continue to push blocks that we have already visited into the stack again and again, and you won't be able to break out of it. And to counter that, all you have to do is you maybe use a Boolean list, or you just simply mark the node that we have already visited. Maybe mark this with a shade of yellow um, to indicate that you have visited that node already. And if you encounter it again, don't push it back on the stack. Uh, Here's another example of a depth search algorithm. So similarly, you will first push A, and then you will look at one of the vertices or one of the edges of A. Let's say we go to D, and then we go to D, we realize there's nothing else. We'll then pop this off, and then we'll examine A again, and then we'll find C. C will proceed on to F. F will then proceed on to B. B will proceed on to E, and then yeah, that's how you will hit every single edge. I do want to note that when you hit B, the reason why we go to E is because while it is connected to A, you have to make sure you want to mark off A here. So then you only be considering E in this case. Um, yeah, that's the approach for depth search. If you want to look at some actual code, I have provided a link to Geeks for Geeks. I didn't want to include it in here to clutter up the slideshow. Okay, so following up depth first search, we have what is known as a breadth first search. And again, like depth first search, the data structure we want to use in this case is a queue. And it differs in a way that instead of going ham and try to put it in like all or nothing way, you just want to sort of radiate outward. In this example, you can't really see it in this example, but if you look at this bigger map, you can see that if you start from the center here, the breadth research will sort of radiates outward until it hits the destination, whereas a depth research will end up looking like a string of line just going to the end and then traversing through like every single corner on its way back. And then if there's no other way of going in like this specific direction, it will sort of like span out this way rather than um, it radiating like this. Okay, so again, like the depth of search, you want to be sure to mark all the different vertices you have visited as you traverse through, because we want to make sure there is no cycles. We want to prevent that as much as possible. Um, so here is a very, very good diagram, in my opinion, of what the difference between like BFS and DFS. So on the left-hand side, we have our depth first search. In this case, let's say we start from A, you sort of just traverse down to B, and then you go all the way down until hit D, but then, or sorry, you go all the way down until you hit H. But in this event, you will then have to go back to B and reanalyze the different vertices, and then check out IE, and then since there isn't a, and then after that you go to J, and then you go backward to B. You do not examine B until you have examined all of its vertices. Um, yeah, and on the other hand, what you'll do for breadth first search is you'll first push A onto the Q, and after you examine it, you'll push B and C, which then will proceed to push on D, E, F, G, and then and then as you examine D, E, F, G, you will proceed to push on the different edges it has or the vertices is connected to onto the Q. So this is the order in a binary search tree of which you will like examine the different edges. Okay. Um, so that is the difference between breadth first search and depth first search. And now I'll talk a little about like when exactly do you use these? Well, in the mage case, it doesn't really matter, but in my opinion, most of the time, a breadth first search is more reliable. Since let's say you have this gigantic graph, if you use a depth first search, since you're branching in so many different way, you might miss out. There might be a shorter solution. Whereas depth first search, you're gonna have to, if you start on the wrong foot, you're gonna have to traverse through this entire half of the graph first before you'll even get to this part. Um, but if you know that the graph itself is like relatively small or it has relatively close direction, it might be more beneficial to use a depth first search over breadth first search. I think either way it will work, but depending on the situation, you will have to sort of like use your own judgment on which algorithm to use in order to traverse the graph. Um, One other part of the path searching algorithm is a bidirectional search. Let's say if we go back to this specific graph, this is now bidirectional since we're only starting from the origin and we're radiating outward. But in this case, what we can do is, what if we had two starting points? We start from the goal and we start from the source as well. If we radiate out from both of these sources, we might be able to cut down the time. But since as they radiate out, they will eventually hit the same node along here, and then we will be able to tell there is a path. And depending on how you implement your algorithm, we will be able to reconstruct this path from the source to the end. And here's a really simple diagram. It's like you have the start and you have the goal, and you're trying to look for where the intercept in order to discover, oh, there is a path from the start to the goal. And this implementation of a search can drastically cut down the amount of time it requires for us to find our goal. Because in this case, if we just use a simple breadth first search, what happens as you're gonna have to examine all these nodes, and let's say there are more nodes over here, you're going to have to examine all of those along with its children until you hit the goal. And by this time, you'll have to fill up all these area on this end and this end before you'll even get close to the goal. Whereas if we simply radiate outward, we can drastically cut down the area. I'm sort of talking about the time complexity in terms of area because you can think of it takes time to just check a node. And let's say these are the nodes that we checked so far, but let's say every one of these is also connected to two other. And then somewhere out there it reconnects back. Then you had to go all the way out here, cover all of these area, which will give you more time complexity, and you're gonna have to go back in. Whereas bidirectional search can give you a really simple answer in just three iteration, as seen in this picture. And lastly, a really helpful algorithm to think about when you do graph problem, especially for the ones that want to optimize a path, is you may want to consider a Dijkstra algorithm. In this case, we are given like the weight of each edges, and the goal of the Dijkstra algorithm is to sort of traverse the different path and then find what is the shortest path. This isn't optimized, so there's like obviously other ways such as A star or other things you can do to calculate the shortest path. But for Dijkstra, essentially what you do is you start by assuming every single node, the time it takes to get to every single node is infinity, and then you start from the starting node. And since you start there, you know the weight or the cost of getting to that point is zero. And then you then begin to traverse the different edges. Um, so in this case, I'm gonna wait for the GIF to restart. So in this case, you start at 1, and then you update all of these nodes to 7, 3, and 6, and then you realize, okay, well, that's the end. So all the vertices, so you change that in permanent, and then you go and check these nodes, and then you double check that, okay, if I reach these vertices, if the value that I have in this path is less than the value it takes, you'll update the value. And after you traverse through all the different vertices it's connected to, you will sort of mark it as red. And by the time you either hit the end or you have finally traversed through every single vertices in the graph, then you know your problem is done, that you don't have to worry about it anymore. Um, yeah, so that is how the Dijkstra algorithm work. And this is essentially the end of the presentation where of the graph algorithm. If you have any question, feel free to send me a message or leave a comment. I will respond. Yep, that's it. Thank you for watching my video.